Okay, so the first section was motion, and we just finished it. Now we're into duration and easing. This is all about the duration, of course, of the animations and the type of the animation. So which kind of easing to use and where.
Mm-hmm.
Okay, so let's do this quickly. This is speed. So they want you to animate stuff quickly so that users don't have to wait.
Mm-hmm.
How frustrating it is when you wait for an interface to do
Yeah.
something. So they're trying to avoid that feeling. Durations should be dynamic. So that means that the durations of the animations shouldn't always be the same. If something travels a shorter distance, the animation should be quicker.
Mm-hmm.
But not only, also they specify objects leaving the screen may have shorter durations as they require less attention.
Mm-hmm.
Yeah. You see, use shorter durations when objects travel short distance or have minor changes in surface area so that the movement doesn't appear too slow.
Mm-hmm.
Because what happens is, usually when you specify an animation, for example, on the web,
Mm-hmm.
when you create an animation, you specify the animation, it's always the same. It's like the animation is 300 milliseconds, for example,
Okay.
and it's not responsive. It doesn't take in consideration how much space should this thing travel.
Mm-hmm.
And that's exactly what they're trying to address here. They're saying if the object you're moving travels much further, give it a bit more time. If instead it's shorter, the distance, make it quicker.
Uh-huh.
So it's like if it's based on the distance traveled rather than on just having an arbitrary duration
Mm-hmm.
for
Mm-hmm.
all of the animations.
Mm-hmm.
Common durations. This is quite interesting. They are trying to explain that depending on the device you are animating the objects on,
Mm-hmm.
you should have different animations.
Mm-hmm.
For example, on watches, on smartwatches, the animations should be very quick, and even on desktop, they should be probably the quickest. They go into quite extensive detail in here, explaining what to use and why. I think it's a bit too much for now to go into this detail,
Mm-hmm.
but you just should be aware of the fact that on mobile, larger screens, tablets, wearables, and desktops, the animations are different,
Mm-hmm.
right? So this is something quite interesting. If you're interested, you can go here and read it all.
Mm-hmm.
Not that it's complex, it's actually quite interesting. For example, tablets, the duration on tablets should be about 30% longer than on mobile, right?
That's
So
interesting because there's not that much size difference or screen space between phone and
Well,
tablet
it's
generally.
probably like, it depends on the tablet, of course,
Yeah,
but it
true.
could be, this one, for example, in this example, the tablet is almost 4 times bigger
Yeah.
than the phone,
Mm-hmm.
right? But that's also because, you see, that's interesting, because objects traveling longer distances on a larger screen have a higher peak velocities than those going shorter distances over the same time period.
Mm-hmm.
So what they're saying is, if you're moving something from left to right on a tablet, it travels a much bigger distance, a much larger distance
Mm.
than the same animation on a phone,
Yeah.
only because the screen
It's bigger.
is bigger.
Mm-hmm. So as a general rule of thumb, the smaller the screen, the quicker the animation.
Yeah, exactly. Larger screens should have longer durations, so that movements aren't too fast, even for your eye to follow the animation,
Okay.
because it travels a much bigger distance.
Mm-hmm.
But then instead on desktop, they almost seem to violate this. On desktop, animation should
that's
be faster
interesting.
and simpler than mobile counterparts. Look at that. Animations here are very subtle and quick. Look at that.
That's so interesting.
Yeah. It's like half of the speed of mobile.
Yeah.
On mobile, it's like 300 milliseconds. On desktop, it's 150. And they explain why. They say because desktop transitions may be less noticeable, they should be immediately responsive and faster than the mobile counterparts. Complex web transitions, so here they're talking about web transitions,
Mm-hmm.
often result in dropped frames unless they're built using GPU acceleration. Shorter durations will make these less noticeable because the animation completes faster. So it's like if they are saying, okay, we know the web technologies aren't there yet, so if you make animations quicker, you don't notice
any errors that may slip through.
On the web, for example, if you are on an older device, animations could feel kind of laggy.
Okay.
Okay, maybe some frame gets dropped. You don't really have control frame by frame.
Okay.
Unless you're using a canvas. I don't want to go technical, but
okay.
okay. So what they're saying is, since you don't know the device this animation will run on,
Just
make it faster so there is less computation,
Okay.
and it will be much better for the users. Okay, this is easing curves. Again, we already saw this before. Difference between a linear animation and an eased animation. So they don't want movement to appear mechanical. How cool is that?
That's interesting.
Motion appears more natural and delightful when acceleration and deceleration occur asymmetrically. This one took me a while at the beginning, but it's quite easy. So if you look at the symmetric ease animation, it's like it starts and the animation starts and ends with the same timing in the symmetric example, okay? So it starts slow and ends slow, but it takes the same time. This is showing the differences in the y-axis and time. So you can see that this curve, in the red curve, takes the same time to complete both the start transition and the end transition. In the asymmetric one instead, you can see that the curve is much steeper at the beginning and much larger at the end. So with asymmetric, they mean this, the differences between the start animation and the end animation. And it feels much more natural when it's asymmetric. So these are different types of curves that they are explaining. This is the standard curve. And here they explain the platform and the protocol to obtain the same kind of curve. Acceleration curve, this is called easing out. Okay? Easing out starts fast and ends slow. The ease in is the opposite. So ease in is used often to show something that goes outside the screen. It's like if it starts slow and travels very fast quickly away from the screen. Let's say you're dragging something and you want to delete a card, you would drag it from left to right, and as you leave it, it will accelerate out of the screen to convey the fact that it's going away. It's not slowing, it's accelerating.
It has no intention of stopping. It's
Exactly.
Exactly what you want it to do.
Yes. This is a sharp curve. Sharp curve is used, as you can see here, they show the screen bounds. So it's like if an element accelerates, but then slows down near the edge of the screen. Imagine it is the edge of the screen. And this can be used for a menu, for example.
Oh, okay. Not to use an example that's not Google, but like the menu at the bottom of Apple computers, where it drops down, but it slowly drops down, so you know it's still there waiting to come back up.
Exactly. That's exactly.
Okay.